Hello everyone! Welcome to this session. My name is Olena. I work at Ivan, where we do a lot with open source technologies. And during this session, I would like to take some of the technologies and look in the context of the contextual search and the vector search. So this session will be full of different demos. We are going to search for movies. We are going also to look for dogs, pictures with the dogs, find some recipes, and also ask a chatbot some kind of a silly and boring questions about documentation. But more importantly, we are going to use vector search for everything of that. So stick with me for the next, how much time we have, around 1 hour, maybe a bit less, and we will learn plenty of things. We will learn, should you use KNN and what actually KNN is, or you should use ANN. What kind of indexing strategies we can apply already with existing vector solutions. What is the best distance metric you can use and what options actually you have. Where to take embeddings, especially for those of you who are still beginning using vector search, so what options you have, and a lot of other things. So plenty to cover. Let's dive in. And let's start with the question, what actually is vector search? And vector search is actually a way to find similarity, so to find related objects that have similar characteristics. And in vector search, we use a machine learning model. So usually you have plenty of different options, we'll cover that later, but you can take a pre-trained model and already apply for your projects. And that model will detect semantic relationships between different things and will distribute those objects in a multidimensional space, knowing those characteristics. And what is interesting, we often don't really know how a model decides that. We train our models, but it's a black box inside of it. So what kind of characteristics it looks at, not always apparent for us humans, but we kind of trust the model to make that relationship. And we talk usually about dimensions, maybe 100,000 dimensions when we are using models, but as humans, sadly, at least I am not so good at thinking about 700-dimensional space. So to simplify, but still show you how a model might map those objects, here I'm using just 2 dimensions. Imagine that it's actually way, way more. And then we can add different objects to that dimension, and those objects, the distance between those objects within the multiple different dimensions will actually show us if for that particular characteristics the objects are close or farther apart. For example, we have some animals, they will be kind of closer to each other. Of course, if you're talking about a spider and a bear, probably they will be still quite apart, but it still can be combined into some of the area farther away from non-animated objects such as guitar. Then when we are talking about money, some maybe credit card and cash, maybe not so far apart from each other, still different objects. And then when we put all our stuff on that multidimensional space, we can have a list of coordinates of those objects. And this is what we are going to use to find the distances, to kind of find which objects are more similar than the others. And here I have kind of those objects as objects, but technically speaking, you can create a vector for anything. It can be a sentence, it can be some kind of a description, can be also a picture. It can be actually done for finding picture of yourself. Maybe you have a big party and you have a lot of photos after that. You can train or like to get the model to find all the pictures with yourself from that party or audio or other things. And to do that, to find those nearest objects, we are using KNN algorithm, so the K-nearest algorithm. And as I mentioned, usually we work with multiple dimensions. So let's say some models can have as little as 300 dimensions, but others would have 700,000 and more. And the more dimensions we have, the more those characteristics we can have. So it gives us better results, but also it's more expensive to run those models. And to start with some example, so that we understand maybe the kind of the most obvious application of vector search, let's look at the movie recommender system. And here the idea is that we are going to use a semantic search to search for the movies. So you might use various words to describe the same concept. And with a vector search, you don't really need to give the precise wording for what you are looking for. You might be looking for a small dog, but call it puppy. So we already have systems which help us with search, but in the kind of, let's say, 10 years ago, what we did to create a lot of synonyms, we would actually have dictionaries which would allow us to replace, look for exact searches, but replace those with some synonyms. With vector search, actually, model does it for us. So this is where we're using for recommendation semantic search. Semantic search in turn can be also implemented quite differently. So I know that, for example, Google uses graph databases, and you can do it in very different ways. The easiest one nowadays is vector search. So because in vector search, you kind of using the work of a model, and often it will be fine to take already trained model, which if you want, you can train additionally on your context. But generally, it's not super complex to do comparing to setting up a graph database for semantic search. Cool. So the system for movie recommender can be described via following diagram. And here, you can actually, like the whole flow will look very similar to the rest of the examples which we have, because generally it's the same steps which we need to perform to start using vector search. So here we are taking the data set. So of course, to search anything, you need to have a data set from where you're going to search those objects. So we are going to take a movie data set. Then we're taking a model. And here, for this particular example, I used TensorFlow Universal Sentence Encoder. This model which I find to be conveniently used with JavaScript. But again, it's one of multiple options we can have. And we process each individual movie, the movie description from the database, dataset, and transform it into a vector. TensorFlow Universal Sentence Encoder gives us vectors of 512 dimensions. And then we need to store those vectors somewhere. And that somewhere should be a database which can work with vectors, which can later help us to compare vectors, again, without trying to write some complex geometrical functions and just rely on that possibility with the vectors, as well as it can work efficiently with the vectors, and we'll see indexing a bit later. So for this particular example, we are going to use Postgres with a PG vector extension. How many of you actually work with Postgres? Oh, wow, that's a lot of hands here. So Postgres, one of many databases which actually, together with the PG vector extension, has the possibility to work with vectors, to compare the vectors, to index the vectors. And what I like about Postgres is because we are already using it so much in so many different contexts, so you don't really need to use any extra database you are not familiar with. You can take the already verified and trusted Postgres database for that. And it actually offers quite a bunch of necessary things which we need for vector search. So OK, so we took the movies, we processed all the movies. Now, in Postgres, we have a table which has those movies. Next, we have a user, someone who is looking what to watch today. And for that, we have a possibility for a user to enter that search phrase. We, again, will convert what user entered into a vector, because we want to compare that single vector now to everything which we have in the database. And here what is important then we use, it's kind of logical, but very important that we should use the same model. So the same TensorFlow model which converted our movies into the vector, we use the same model to convert the search phrase into the vector because we want to compare apples to apples. Different models will have different way how they will identify the characteristics. Even if you have two models and they both have the same number of dimensions, this doesn't mean that they are comparable. Oops. With that, I also, okay. So this is a data set which I found for the movie plots. So this is from Wikipedia. And there are just like very, very convenient. And I appreciate taking the pictures, but I also will leave the GitHub repositories and all the links later. Take the pictures, go ahead. But I will combine it all and share with you so that you don't have to try to guess these links from the slides. So, and we have the information about the plot, and that's what I actually convert into the vector. The amount of data which we convert into the vector matters, because models usually have a limit which amount of information you can actually give it for the vector. And if the limit is more than the limit, usually you have to chunk it into parts and then process it separately. Cool. So that's a GitHub repository which I will share later. In case you will be interested in any of the demos which I'm showing, you will be able to look into more details in the code later. Just find it a bit helpful. So the first one with the movie recommender, I actually use JavaScript. JavaScript is not the most popular language when it comes to the machine learning. Of course, the king there is Python, but still you can use JavaScript with TensorFlow. There are other frameworks and libraries which can help you as well. I found TensorFlow, even though it's not super friendly, with all honesty, it's actually better than other alternatives. For that, so like I will start with this chunk of code. So this is JavaScript, and I don't see so many of you, but could you raise your hand if you're actually familiar with JavaScript or like you worked? Okay, we have, okay, good. You understand it. Amazing. So this is a piece of code which we can use to transform a single movie plot or any single piece of text into a vector. So here we are taking the model, and I'm using the TensorFlow Universal Sentence Encoder model, which transforms any text you give into numbers. And if I will run that code, it will produce us an array of floats which will indicate the position of that movie, how that model will position that particular text on a multi-dimensional space. This is for one movie, of course. We need to process all the data. So what you will take for that, and here's an example with the Postgres, you will connect to Postgres. You need to enable the extension. There are a bit more steps I'm using here, or like in this example, I was using Ivan for Postgres. That's why we have it pre-installed. I just had to run create extension, which kind of enables it, but doesn't really need to create it even. And once we enable the extension, the PG vector, because all the magic here when it comes to the vectors, working with vectors, is in the PG vector. Without PG vector, Postgres sadly doesn't know about how to work with those numbers. But once you have it enabled, we get a new type of a property, which is called vector. And when you define your table, for example, you need to specify that you will have a field embedding of type vector with a number of dimensions equal to 512. And once you have that, you can now process all the movies, kind of similar to how we did it with a single one. Just now, to process it all together, I also recommend to use some kind of batching here. I'm using here PG promise. and I am just kind of processing the whole data set, and it has like 35,000 movies in and storing it in the Postgres. So if you will decide to run that GitHub repository, you will see something like this, like processing the data gradually. Running, of course, model, running the whole computation is not super fast. So it's not slow either, but using AI doesn't come for free in any case. So once we store the data in the Postgres, so once we have that, we go to the stage number 2, and now we would like to find the nearest movie. So pretending that we are a user, and here the test phrase I have on the slide is a lot of cute puppies, assuming that majority of you at least like cute puppies. So we run that query. So this is JavaScript code. But if you ignore the JavaScript part and we just look at the Postgres query, because this is actually where the instruction to Postgres that we would like to search, we would like to use vector search, and then we would like to find 5 closest movie plots to the test phrase vector which we provided. And we also use this kind of a cute element which indicates that we are using here L2 distance. We'll look at different types of distances a bit later, but this is just how PG vector it reduced different distances, and then kind of how it works with the vector search. And then if we run this, we get a lot of a wall of text, but we retrieve the nearest 5 movies, and The Secret Life of Pets, and all of the rest. And what is interesting, so we were searching for puppies, but it doesn't really have to have like puppies in that text. Anything related to pets or dogs will be still close enough according to the model. And again, this is just I added like a simple interface on top of it. So for the first request, it will take some time, but actually, like, and this is a bit of playing with Next.js. Eventually, it actually gets faster. However, even though this performance looks good enough, we just have 40K or like 35K movies. If we had way more items in our dataset, this logic would not be enough. This would be a bit too slow, because what actually we are doing here is a brute force, comparing our test vector to all 35K items in the database, which some databases do faster than others, but in any case, let's say if you are at one of those Google interviews, the brute force is only the first step, then you want to optimize so that you don't have to analyze all the data. And this brings me to a topic of KNN versus ANN. So K nearest neighbors algorithm is where we are comparing all of the items to our text phrase. But the ANN is approximate nearest neighbor. And the difference between them happens at the prediction phase. So ANN will only take a small fraction of the data and will analyze only that fraction, versus KNN will just look at all the data. KNN is really good and very precise. If not for the performance, you actually want to use KNN, because it will definitely look at all the items and find you the best, the closest, the real closest neighbors. However, it can take ages. So generally, we prefer to use ANN. And for ANN, for the approximation algorithms, so it's kind of creating an index. Oops, my clicker stopped working. We have a variety of index types. And for example, in PG vector, which we just looked at, there are 2 indexes which we can use. And I actually really like those 2 indexes, because in a way they are quite different, and they are have preferences for different types of scenarios. So let's look at them, at their pros and cons, and also to understand how exactly in vector search we are using indexes and how exactly we aim at speeding up the search, because those indexes work somewhat differently from a usual index which you will see in Postgres. And the first index is called inverted file with flat compression. So imagining that these points we have are the points in our multidimensional space. What we want to do, we want to split that multidimensional space into chunks. And how we do it? We create a number of centroids. So having enough data, we are setting up centroids in that space. And then we find the clusters around those centroids. And elements of those clusters will become the vectors that kind of create that area into which we split the stuff. And from now on, we don't really have to search everything. We can only search some of the clusters and omit other clusters so that it is faster. And for this particular index, we define the number of clusters which we want to have. Here it's the lists. And as well, we can define how many of the clusters you actually want to search when you are doing that vector search with indexing. So number of probes. Obviously, the more clusters you have and the less items per cluster you have to search, the faster will be the vector search. But then you have actually this danger of accidentally missing the closest neighbors because they belong to a different cluster. So you need really like to find the balance and find like better recall so that you are efficient, but also you are not losing a crazy amount of data by being imprecise and getting some of those really fake nearest neighbors. So this is the index number 1, has an advantage of being somewhat simple to understand and also quick to use and set up. Has some disadvantages to which we will come in a second. But before that, let's look at a different index. So this one called Hierarchical Navigatable Small Worlds. Amazing name. So it actually splits our data into layers. And it creates, or let's say it doesn't really split the data, it creates the layers and then positions our data like kind of zooming in. So the lower you go, the more you zoom into the data, or if you go out, you zoom out from the data. So you can navigate through the layers one by one to find exactly what you need. With this particular index, you need to define also a couple of parameters which might indicate how much effort or how much granularity will be in the index. This particular index I find way more popular when being used because it actually is faster. Or let's say the whole search process is faster. But preparation of the index can take time. And for example, the EF construction, it will be the number of connections per layer. So the better numbers you set, the more time you need to spend creating this index. Yes, so between those two indexes, the H and SW, which I often see being used because it's actually faster. However, it's more computationally expensive, and you need to have a server cluster which allows you to run it. Ivy flat is almost ideal, but Ivy flat, because when we create those clusters, when we divide the space, we have this challenge. If you're going to change the data on a frequent interval, if you're going to remove some records, if you're going to add more, you need to recalculate those subclusters again and again. Otherwise, you end up actually not catching the real data. And H and SW doesn't have that limitations. So yeah, so you need to be like to look at your data. Maybe if you don't have a huge data set and you don't change it very frequently, then I would recommend to use Ivy flat. Kind of it's very lightweight. But if you need a good performance or like performance for you matters, then use HNSW. So I mentioned a couple of times the recall concept. And apart from the performance, which we of course want to increase, we do care about the recall. And recall actually it's how many the neighbors which we retrieved during that search are the true nearest neighbor. So recall actually specifies the quality of our results. How many, what we search is actually relevant and not like, like random items from another side of the dimensions. So if you have a recall of 1, it means that 100% of what you retrieved is the real nearest neighbors. If you have 0.5, it means only 50%, and the rest are something which you don't really want to have in the search result. And by using the indexes, of course, we are approximating stuff. So by default, if you use KNN, like the original one, the brute force, you will most probably, you will get better results. You will get the real nearest neighbors. With approximation, you might lose in that domain. However, again, it's a trade-off. Cool. That was a lot of boring theoretical part. Let's move to another demo. And this particular one I find pretty funny because it actually uses not only text, but also uses images. And I like the images in this particular one because, so technically, model can be trained not only on the text. The model can actually understand or kind of, let's say understand the images and how it relates to text. So we ask a model to process a picture of a dog. It will create some particular item on this multidimensional space. And when we just type a dog, it will create also a dot on the multidimensional space, which is not so far from the picture of the dog. Same can be done to the sounds, to videos, but this is example where we are using images. And for this particular example, I am taking pictures from Unsplash. They have a huge data set, very nice to play with. And then we do with the pictures the same thing which we did to the movies. So we take a model, and this model is actually a clip model from OpenAI, and we run that model and transform each of the pictures into a vector. It also has 512 dimensions, but again, those models are different. You can't really compare vectors across them. And then I'm storing the data, and this time I'm using OpenSearch. I love OpenSearch for all the visualizations you can do. It's like super amazing database, but also it supports vector search, also has indexing and all that stuff. So if you're already working with OpenSearch, OpenSearch is a bit different from Postgres because in Postgres we assume that the data will be modified on a regular basis. With OpenSearch, we usually say it should be not exactly super immutable, but we prefer not to change the data very frequently. So again, depends on your use case. Then, similarly to the movies, we take a search phrase. And by the way, this example I have seen in Trello. If you use Trello boards, you have this possibility to select the background. And they are like, OK, you can search for the backgrounds which you want to have. And they're using the Unsplash dataset as well, because I can recognize those images. And you type, I want to see an airplane, an airport or something, and then it kind of shows you those pictures. So it kind of works in the same way. So you take a search phrase. We, again, use the same model. We convert the search phrase into a vector. And then we compare that vector to the rest of the vectors, to the rest of the images. And that returns us the nearest values in the database. So the OpenSearch, and if I can ask, could you raise your hand if you ever worked with OpenSearch in some way? OK, I see 1, 2, 3. the third one was probably not so sure, but Elasticsearch actually, have you? Oh, okay, cool. Oh, that's actually where I should have started. So some 3 years ago, when Elastic changed the license, that actually was where the OpenSearch was born. So if you remember, so of course, like Elasticsearch and OpenSearch, they are moving their own direction, so you can't really compare them anymore. But 3 years ago, they had the same origin. Cool, so if you're familiar with Elasticsearch, you probably will kind of at least recognize some of that code, even though the KNN in Elastic and in OpenSearch works differently. So here we indicate that when we create an index, we want to have enabled KNN search, and also OpenSearch wants to know as well how many dimensions it should expect in your data. And once we have that, we can load the model. So here I'm actually using Python. I'll touch this a bit later. But let's say Python is, I know it's not a Python audience here, but Python is makes life so way easier when working with machine learning. And here I'm taking this model, I'm using Python, and then run the images, and I will get the embeddings for each of the images. And then when we have the data stored in OpenSearch, we want to send a query which uses KNN here, and to find, for example, in this particular example, is like k is equal to 2, so I want to find 2 nearest neighbors. And in the database, in the OpenSearch, what I actually store, I don't store images there, but I kind of have the images when I process the data, and there I'm just storing the IDs or URLs to the images so that I can retrieve the image later. When I search for it, it gives me the URL, and I just visualize it. And this is like a notebook. I also have an article written on this if you are more curious to learn it and do it yourself. Again, I will link to that later. So this is a multidimensional, multi-modal search, which I find to be really useful, and it opens so many different possibilities when working with data. And while we are at this, I would like to show how exactly we are comparing those vectors. So imagine when we have this bunch of records stored in OpenSearch, and then we have the search phrase, and we need to find the distance from the search phrase to all of those vectors, or if you are using index, and kind of to part of those. But for this, we need some kind of metrics, and to have this distance between those vectors. And there are various options. So different vector databases will have different set of the metrics which we can use. However, most of them have like overlap. For example, the Euclidean distance, the L2 distance, will be present in almost all of the vector search, of the vector databases. And it's also the easiest to understand, because technically it's a straight line from point A to point B. If we know coordinates, we can calculate. We need to take a square root of the things. So it's this metric is kind of cool, but on the other hand, has a couple of disadvantages. First of all, it's actually computationally more expensive than some other metrics, because we need to take a square root. And if you can imagine that we have huge amount of dimensions, that can be quite expensive. But secondly, because we are taking squares of the values, we can get outliers, because especially if we have not exactly normalized data set, some of the values can become significantly bigger because we are taking a square of between the coordinates. So it's considered to be somewhat sensitive to outliers. You might want to be a bit more careful, even though it's still a solid and good metric, especially if you don't really care so much, or like if it's within your performance range. We also have L1 norm, which is quite interesting. It's more resilient to outliers. This is comes from the name of the grid layer of New York. So you can't go directly unless you are flying in a helicopter. But if you're taking a taxi, you have to kind of make turns. And here we are not taking squares or anything. It's kind of easier. We just calculate this distance you need to get. It's less precise. It's also not as frequently used as L2, but it actually kind of faster. And then based on that, or not based, like connected, we have this L infinity, which is also not as frequently used, but it's quite interesting because it kind of measures the maximum absolute distance between the coordinates, between different dimensions. So it looks for worst case scenarios where you're like, okay, what will be the dimension which gives me the biggest distance between those values? So you can use it, for example, to emphasize some of the dominant features between the values. It's actually way more frequently applicable in image processing, for example. But still, it's kind of interesting one, and you can always play with those metrics to see if some of those will be better for your particular scenario. The metric, or actually it's not exactly metric, but the way how we can calculate the distance, we can use the cosine similarity. This one is super popular. And actually this one might be the best, from at least what I read, for when you analyze text. So if you are doing a vector search and we are doing it based on the text, remember cosine similarity and try it out. It might give you better results even than L2. And also it is somewhat cheaper to perform computationally. But here we are only looking at the angle. So in case your data set is a bit chaotic, again, might not really happen, but if it's a bit chaotic and you have significant differences between the values of those vectors, then you might have a bit of an issue because we are only looking at the angle. You can imagine that some vectors can be kind of distance in the space will be bigger, but the angle will be still the same. So, so here then instead of cosine similarity, you might consider using inner product, another very, very popular way of calculating the distances by projecting one vector onto another vector. But if you have normalized data, then cosine similarity will give you the same result as inner product. Inner product is only when you have different magnitudes of the vectors. Most of the models, I think they will give you good, clean, nicely arranged data. And for example, cosine, L2, dot product, they probably is the most used metrics in vector search. However, when you're working with the model, what I would do, I would go and check the model you use. Do they recommend any particular metric for that particular data? Because that actually can be a hint which one you should use. And also, I would look at the performance, and that's maybe another hint how to see, and I don't know, like also like recalling how well those objects are connected, and if one metric gives you better results than other. Another thing for the performance which you can use is to use the filtering. So, and make stuff faster with the filtering. For example, if you have not only information about the movies, but you have some metadata, and we actually had the metadata also in that data set, you might have the, I don't know, like something more like a length of the movie or the language of something else. So you might want to combine the vector search and the structured search. And you can do it in several different ways. So first of all, you can do some kind of a pre-filtering. So you just need to take then that metadata and then apply that filter, the strict filter, and kind of eliminate unnecessary items. And then based on what you have left, you run the vector search. This is not bad. However, if you do that, you are ruining the indexes most of the time. So then you cannot rely on the index. Of course, if you know that by using the strict search, you minimizing so much the number of data in the data sets which are relevant to you, and maybe actually you don't really care anymore about the index, it will be fast anyway. But in case your strict search doesn't remove that big amount of data and you end up still with hundreds of thousands of records, that might be problematic because maybe rebuilding the index would make sense at that point of time. So this might scale poorly. Then we have the post filtering, which I honestly see less and I also like it a bit less. This is if we first perform the vector search on the data set, so we just perform maybe that vector search on the movies, and then we just filter the movies by extra categories which the user is interested in. But then we can't really predict if a user wants to see 10 results at the end. We might have cleaned a lot of results through the vector search, so in the end we don't have much to give to the user. So you need to be careful with post filtering. The third alternative, which I know exists in OpenSearch, and I think it becomes interesting in other solutions, is at least what OpenSearch calls efficient filtering. So this is where you actually give that power to OpenSearch to decide how to combine a filter, and let me show you an example, how to combine a filtering with the vector search. And here is like a Boolean condition, so like some kind of range condition, and then on top you have the vector search. What vector search would do here, it will actually try to use its logic to understand what will be better, pre-filtering or post-filtering, and what to do with the index. So when we used this kind of a filtering, I know that one of our customers used it, they saw a significant improvement. Of course, you can manually try to decide which one to use, but again, it can really depend on the query, and OpenSearch does some kind of calculation of those filter IDs and kind of doing some logic behind the scenes which you don't really want to re-implement. So if your vector search database supports this efficient filtering, or however it's called, then I would go for that. And combining with filtering can really actually also improve the speed of the query. Cool. So we talked about OpenSearch. We talked about Postgres. How many of you know about ClickHouse? Could you raise your hand? ClickHouse as a columnar database. I see some hands. It's really amazing. So ClickHouse, the next example I wanted to show, because ClickHouse also can work with vectors. Actually, ClickHouse is very powerful for all the scientific computations and all those mathematical formulas. So it can do a lot of things apart from vector search. But I find that in vector search, it's quite an interesting solution as well. For those of you who are not familiar with ClickHouse, ClickHouse is not row-oriented database. It's a column-oriented database. So we store data in columns, and we usually use it for analytics. It's super fast, just how, like the indexes, for example, in ClickHouse, they don't index every row. They index chunks of data. They work with blocks of 10,000 items. So ClickHouse is just marvelous technology when it comes to kind of the way how it's optimized. So anyway, this particular example, I took the list of recipes, and I used a model from Hugging Face. I just wanted to show something from Hugging Face, because Hugging Face is actually, again, this is a bit of a Python thingy, but Hugging Face contains so many, it's a hub to store the models, and there you can really search, compare. This particular model is on minimalistic side because it has only 384 dimensions. But again, so there, when you are looking for a model, you can really see what it was trained on and so on. So we do the same stuff as we were doing before, but now we're doing for the recipes. And then we compare a single vector to the rest of the stuff. So this is a model. What I also like, because I am not a Python developer, I'm actually a JavaScript developer who has to use sometimes Python or Java or other languages. But what I appreciate, and for those of you who will be experimenting, you don't have to be super afraid of Python code, because they are given really good examples, and you can select again the model. Depending on your use case, you will see what data it was trained on, so that you, because also like what I didn't mention, when we are selecting a model for vector search, you really actually want to align it with the purpose of the model. Because if the model was trained, I don't know, on the Twitter messages, and you're like, okay, let me just take my scientific database and let's see what model will come up with, you can imagine it will just give you some rubbish connections between objects. So you want use proper models which was trained on kind of an area which is not far away from what you have. You can also additionally train, you can take some kind of a basic model and then give it additional information and train and evolve on the data. Cool, so with the ClickHouse example, I took those recipes, I had to transform a bit the data, I moved it to Parquet file because I think nowadays we use Parquet for big data, is way more efficient than JSON. And in the end, so this is a code more or less of how we define create a table in ClickHouse. It's very similar to normal SQL. And then we can enter the data, the recipes. So it's all kind of works as usual. There is a lot of logic in ClickHouse behind the scenes, how exactly it processes the data, but it's super, super fast. And then there are a number of functions. Here I'm using L2 distance, and then I'm calculating the distance and getting those nearest recipes. So the number of distances, because ClickHouse is very focused on the scientific aspect of the data, there are, like, I think, more options for the distances. But again, you get the L2 distance, the cosine distance, all the usual stuff. What is interesting about ClickHouse is that right now, the indexes it supports is only in the experimental mode. However, based on my experience, it actually works faster with the data just by the way how it actually processes the data and how it analyzes. You may expect that ClickHouse will be faster than, for example, Postgres with an index. This is just the nature of columnar databases versus row-based database. And also injecting the data into ClickHouse is so way faster than, for example, into PG. Again, it's not that PG is bad, it's just like different. If you're working with analytical data, you might want to try ClickHouse. Cool. The last example I wanted to show is about the retrieval augmented generation of this RAG pattern, which I see being used more and more frequently. And it's kind of creating a chatbot based on large language model. And the thing that we use large language models right now on a daily basis. But training a large language model is expensive, and also it takes time. We are getting better and better with it, but it's not something which you kind of like, oh, let me leave it for 2 hours and it's done. No. So there are different use cases where, first of all, you don't want to give the data to the large language model to be trained on. Maybe it's like some user-related private information. Or maybe it's a data which is very, very recent, and you want to expand the knowledge of the large language model on that data. Or maybe it's kind of this real-time context, like the rain or something else like which is happening right now. So, and in this example, again, I will provide the link to kind of an article in GitHub repository where we have the code. But this is an example where, assuming that a large language model does, and I was communicating with the Bedrock, doesn't know much about the documentation of Ivan. And I'm very sorry for a very boring example in this case, but still. So what I did, I took the documentation which we have to Ivan, and I gave it as addition to this large language model so that it could answer my question using its capability of kind of talking and coming up with all this text, but using the source of the data from the external source which I provided. This particular example uses AWS, and we can split it into 2 parts, kind of also similarly to how we did before. The first part will be the data ingestion, And this is where we need to generate those embeddings from the existing data source set or some kind of a data corpus. And we store the data in the database. Here I also used OpenSearch. Because again, it can work with vector. We could use something else here. Doesn't have to be OpenSearch. As well as for more, actually, technically, all those is like Lego. You could use all different items here. And the second part was data retrieval, where we actually perform that vector search and we combine it with the request to large language model. So for those of you who work with AWS and interested in this particular code, I had a SAM template. Generally, I enjoyed using the serverless approach with the Amazon Bedrock because then it meant I didn't have to run the model somewhere in the cloud. And running the model constantly, if you don't make a lot of requests, is pretty expensive. The data ingestion part. During the data ingestion part, as I mentioned, I used like the documentation parts. So we split it into smaller chunks and then put it into L3 bucket. Doesn't have to be this particular. You could actually get the data in, I don't know, like from the Apache Kafka stream or something else. But you need somewhere data. So the idea was that whenever we send the data into S3, what we can do, we can attach an event. So here it was SQS. So it gives a notification to SQS, and SQS can take the data and in turn run the data on the Lambda. Again, this depends on your particular architecture. For me, it was like, how do I set the flow of the data into OpenSearch? So with the Lambda, what I could do then, I can take that piece of data, the text in the document, and I can process it using the LangChain. So there are different ways how you can work with models. LangChain simplifies this RAG pattern significantly. So I would recommend, if you are working with the RAG solutions, then try LangChain. It's available in different languages, JavaScript, Python, Java. .NET, I'm not sure, should have checked, but maybe it also supports something there. And what we do means the Lambda handler to process the data. We take the file name, we get the records from there, we use the bedrock embedding to get the embedding itself, and we store that vector in OpenSearch. And then in the OpenSearch, generally, we get all that information. This is OpenSearch dashboard, and we can check what kind of vectors we have and what is the text for that vector. So that's what we have in the database. Once we have that, similarly to how we did it with the movies, now we can do the data retrieval. And in the data retrieval, it's a Lambda model. But here, it will be a bit different. First of all, I had to use JavaScript here. So it's a bit of a mix, I'm sorry for that, of languages. It's like a salad. But this particular one, I wanted to use the streamified response. So you know like how when ChatGPT talks to you, it's kind of, you see these chunks of information it produces. So it actually kind of creates a chain of the data. And so far, when I was using the lambdas from AWS, only JavaScript 1 was supporting that. Maybe there will be something else later. So here the idea is that we are creating a prompt to the language model, and we create that chain, but also we provide information from the vector database in addition to the question which we sent to the large language model. And then it combines that information. I had also to specify that from that LLM that please use the additional data I provided you. Don't try to get it from your own knowledge, but it's just because I didn't know actually if that LLM already familiar with Ivan, and I wanted just to have it like pure, using LLM for the case of like just talking, but using my data to give the correct information. So this is a large language model with vector search. There are some caveats here. Let's say we often try to use RAG pattern to eliminate hallucinations of large language models. But also, if you are not doing it correctly, if your data is not really good in those vectors, you might increase the number of hallucinations. So you need to be very careful, but it's super popular right now approach and many different applications. Okay, the last thing I wanted to share with you, just an ideas. For those of you who are just starting with the embeddings, if you are fine with Python, try out Python. Hugging Face has really amazing set of all the models, and it's actually very, very easy to use. And they update the libraries on a frequent basis, so you might actually try to run the code you created yesterday and fails. But apart from that, inconvenience, because it just moves so fast, it's actually a very solid solution. It's easy to use, at least comparing to other options which I tried, for example, with JavaScript. But if you are into JavaScript or Java, TensorFlow, still solid one, might have a bit of a headaches. Then if you don't really want to write that code, but you are fine with working with APIs, you can use OpenAI models, you can use Amazon Bedrock, you can run the models in SageMaker. Yeah, and if you are working with the Retrieval augmented generation, look into LangChain, because that one will save you plenty of time. This is kind of the best of the best solutions we have right now. Yes, I wanted to show. Yeah, and for example, if you are working with Hugging Face, you can look at how to deploy the model. For example, they have already example for, I'm using from time to time SageMaker. You just copy, run it in the SageMaker, and it actually deploys your model. It's probably like for the production environments, you want to do some extra steps, but at least if you are experimenting for the playground, it's easy to start. Just don't forget to clean that stuff later, so that you are not wasting a lot of money. And some code for the Java, but it's probably less important. So I want to leave you with a couple of links. First of all, if you want to try any of the data solutions which I showed and have extra credits, that gives you for the PG, we have a platform at Ivan which integrates all those solutions together. It's easy to use, easy to set up, and we also have free tier for Postgres, so it's quite convenient. Postgres, MySQL, and Redis, that's where we have free tiers. And second, the links, this is a GitHub repository with a bunch of links to different solutions which I was showing. On a regular basis, we are doing that workshop with TensorFlow and Movie Recommender. It will be also tomorrow. So you can, if you are interested, on the Ivan page, there will be the link to that, or just talk to me and I will share with you the link to that workshop. And for the rest of the demos, in one or other way, I have links there. So that's what I wanted to cover with you today. And I think I have 2 minutes extra for any questions you have. Or I will be also around in case you want to catch me later and talk about vector search. Thank you.